This lab is called Equilibrium Water Games. And in it, we're going to serve as a short introduction to equilibrium using water transferring between two beakers as our model. We have two large beakers, 600 milliliter sizes, and one of them is filled to the 500 milliliter mark. In part one of the procedure, we're going to use the 50 milliliter beaker to transfer water from beakers, the large beaker A to beaker B. The other beaker is a really tiny 10 milliliter beaker that will be used to transfer water from the large beaker B to beaker A. Now, the rule is you can't tip the large beakers. You've got to let them be exactly as they are. And we're going to record a lot of volumes. So if you look at the data table, there's quite a bit here. The initial, so in part one data, we're on the left side. The initial volume of water in beaker A is 500 milliliters. We have 0 milliliters in beaker B. This one's empty. This one's got 500 mils of water. Now we're going to dip. You can dip your transfer beaker in as much as you want and transfer water over. Try to minimize splashing, but we understand if that happens, it happens. And then a transfer cycle includes both the attempt to transfer water from beaker A to B, but also the attempt to transfer water from beakers B to A. Now you might say, hey, you couldn't, whereas you could fill the 50 milliliter beaker, you couldn't really fill the 10 milliliter beaker. Yeah, that's a built-in part of this lab, is that you can't, oftentimes when the water level's low, you can't actually fill your transfer beaker. So we've completed a transfer cycle. We've moved some water from large beaker A to large beaker B, and we've moved some water from large beaker B back to beaker A. Let's record the volumes. After completing that transfer, and I'm kind of roughing this in, we're using the volume markings on the side of the beaker here. I'd say we have 450 milliliters of water in beaker A and about 80 milliliters of water in beaker B. Okay, and don't worry if the numbers don't quite add up to 500, like right off the bat I'm saying, hey, wait a minute, somehow the total of water right now is more than 500. It's all going to work out in the end, so don't worry about that. Okay, I'm going to try transfer cycle 2, moving as much water as I can from beaker A to B, and then as much water as I can from beaker B to back to A, trying to get it as full as I can. Get a little more water this time. And now the new volumes after transfer cycle 2, I'd say we're at 400 milliliters in beaker A, and I'm going to put that at 110 milliliters of water in beaker B. That's after transfer cycle 2. Now for transfer cycle C, I'm putting as much water as I can in the 50 milliliter size beaker and transferring it. And then now I'm getting a much fuller amount of water in the teeny tiny beaker and transferring that and recording now our volumes after transfer cycle 3. I'd say I've got 360 milliliters of water in A and 150 in beaker B. Again, we'll do another transfer cycle. Don't worry about splashing, it happens. Part of this challenge here is the size of your hands. If you have smaller hands, it works better. Okay, after transfer cycle 4, I've got 320 milliliters in A and in 195 in beaker B. Another transfer cycle. I've got now 280 in beaker A and 240 in beaker B. That's after transfer cycle 5. Now we'll do transfer cycle 6. Oops. Okay. After 6, I've got 240 in beaker A and 280 in beaker B. After transfer cycle 7, I now have 200 in beaker A, 320 in beaker B. And now it's getting harder and harder to fill that 50 milliliter size beaker. I cannot fill it now. But I can still fill the 10 milliliter size beaker. After transfer cycle 8, I've got 160 in beaker A and 350 in beaker B. And now I'm definitely not filling the bigger of the transfer beakers, but still doing the best we can. After cycle 9, we're at 140 for beaker A and 380 for beaker B. And now I'm getting even less in the larger beaker. After transfer cycle 10, we've got, let's say, 110 milliliters in beaker A and an even 400 in beaker B. Only getting a little water now. And I'd say we're down to 100 milliliters even in beaker A and 410 in beaker B. I'd say we're at 95 milliliters in beaker A. This is after transfer cycle 12. And we're at 420 milliliters in beaker B. And then you might say, what's the point here, Mr. Gaffey? Students, eventually we're going to hit an equilibrium in the transfer process. Okay, after that one, I'd say we're at 95 milliliters in beaker A, and we're still at 420 in beaker B. Let's try one more time here. And again, so we're at transfer cycle, after transfer cycle 14, we're still at 95 milliliters in beaker A, 420 milliliters in beaker B. And because our numbers were the same for 3 consecutive transfer cycles, we can stop. We're at a point now where we've got the data we need, and we've reached an equilibrium, so you don't need to continue with transfer cycles. We're going to talk about what that means in the board work later. Now for part 2 of the lab, it says repeat your procedure, except instead of starting with 500 milliliters in beaker A and 0 milliliters in beaker B, we want you to start with 250 milliliters in each. So now our beakers, or the large beakers, have the same amount of water. Let's see what happens. Are we going to reach the same equilibrium? Are we going to reach it quicker? Are we going to reach it less quickly? Don't know. Let's find out. So now we're going to fill out the data in part 2, so the right column. Initially, The volume in beaker A is 250 milliliters, and beaker B also 250. And let's do the same procedure. We're transferring as much water as we can from A to B with the 50 milliliter size beaker, and then from B to A with the 10 milliliter size beaker. And in each of those, moving from one side to the next and then back is a transfer cycle. Okay, so after transfer cycle 1, in beaker A, we're at 210 milliliters, and in beaker B, 290. Let's try again. Trying to minimize the spilling, but also realizing that that's part of lab is spilling. Okay, after transfer cycle 2, we've got 180 milliliters in beaker A, and I'd say 330 in beaker B. And after transfer cycle 3, we're down to 140. Let's call it 145. 145 in beaker A, and 365 in beaker B. I'll have all these numbers on the board for you to look at shortly. After transfer cycle 4, our numbers are about 120 in beaker A and 390 in beaker B. And now I'm getting a lot less water in my transfer beaker than I was at first. After transfer cycle 5, we're at 100 in beaker A and 400 in beaker B. And I'd say we're at 90 in beaker. This is after transfer cycle 6. 90 in beaker A and 410 in beaker B. After transfer cycle 6, oh, well, we're still at 90 and 410. We may have reached equilibrium here. Let's do it one more time to make sure. Getting as much water as I can from beaker A, transferring as much water as we can from beaker B. And again, 90 and 410. So we've now reached equilibrium. You could keep doing this until the end of the day, and you'd still get the same, roughly the same measurements of volume, 90 and 410. So let's stop here. I'll put the data table on the board so you can see it visually, and then we'll tackle the analysis questions. So here's a look at our data written out on the board. Notice that in the part 1 portion of the lab, where we had 500 milliliters in beaker A and none in beaker B, it took more transfer cycles to reach equilibrium than it did in part 2. The point at which the water levels stopped changing substantially, and keep in mind, we were just the beaker measurements on the sides of the beaker resulted in some rough estimation, but that's okay. We only need to know roughly when did this happen? When did equilibrium get established? And I would say in part 1 data, it was in after transfer cycle 12. And in the part 2 data, it was after transfer cycle 6, because then it started repeating and it could have kept going on, and you would just get the same numbers. Okay, so with that as our background, and by the way, notice how similar these numbers are. 95 milliliters in beaker A, 420 in beaker B, 90 in beaker A, and 410 in beaker B. Those are some pretty similar numbers. Oh, one other thing to point out. When you add the two numbers in beakers A and B throughout any of these transfer cycles, theoretically, you should hit 500 on the nose, right? Because in each case, we started with a total of 500 milliliters of water. They may have been divided differently between beakers A and B, but we had a sum total of 500 mils of water. Well, number one, sometimes water spills out. And number two, like looking after transfer cycle 1 in part 1 data, the sum total is 530 milliliters of water. And you might say, where did the extra 30 milliliters of water come from? Due to my inaccurate measurement of the volume. I was eyeballing it, and I called a number, and that's okay. Sometimes scientists do that. It's okay. We're still going to get a lot of good information from this. Okay, looking at the analysis questions. Number 1, look at your part 1 data. After which transfer cycle did the water level stop changing? So if you remember what we had noted on our data table, for part 1, equilibrium was established after transfer cycle 12. Question 1b, calculate the ratio of volume of water in beaker B over volume of water in beaker A at that point. So we're going to do B over A. And the numbers from our part 1 data, once equilibrium was established, was 420 and 95. Let's punch those numbers into a calculator and write down the ratio. So 420 over 95, I get roughly 4.4. Okay, analysis question 2. It's going to be the same question, but looking at part 2 data. Our equilibrium was established this time much more quickly. When we had an even distribution of water in the two beakers to begin with, it didn't take as many transfer cycles to get the water moved over into beaker B as it did in the part 1 data. Okay, so this happened after transfer cycle 9. I'm sorry, 6, after transfer cycle number 6. And our ratio of volume in beaker B over A, we can calculate. At the end of that, once equilibrium had been established, it was 410 milliliters in B over 90 in A. So let's punch that into our calculator. 410 over 90.
Dismissing students at this time. Thank you.
And I get 4.6 as the ratio. You don't need units for a ratio. So 4.4 as compared to 4.6. That's interesting. So question 3 is actually going to get us to compare your part 1 data to part 2 data. I would say there's very little difference in the ratios. In other words, this number is quite similar to that number. I mean, within 0.2. So that's quite good. Now let's move on to the next 2 analysis questions, which ask us to think a little more broadly about this experiment. Question 4. This experiment uses water to simulate the movement of reactant and product molecules in a reversible chemical equation. Large beaker A represents the reactants. Large beaker B represents the products. Question A, how do we know that equilibrium has been established? Well, in this case, the water levels stabilized. Or that's another way of saying stopped changing. They stopped changing. Question B, what does the volume of the water in the beakers represent? Well, if we're picturing this as modeling a chemical equation, the volume of the water represents the concentration of the chemicals. So when we say that the volume of water in beaker A is staying the same and the volume of water in beaker B is staying the same, that means that the concentration of the reactant chemicals and the concentration of the product chemicals in the simulation have leveled off. They're not changing anymore. Question 5, describe one source of error in this lab. Well, students, no matter how good you are at performing this experiment, some water is going to spill out of the beakers as you transfer. It's absolutely going to happen, no matter how good you are. So that's one source of error. Another one is the very crude volume metrics. We could have used something like a round bottom flask or a graduated cylinder, which has much more precise volume markings. So there were, as I pointed out earlier, transfer cycles where the sum total of the volumes exceeded 500 milliliters in my case. I was doing the best I could with some estimating, and you know what, it didn't affect too much anything that we conclude from that, other than to say, hey, listen, we reached equilibrium at the same ratio of reactants and products. Isn't that interesting? Isn't that curious about using a 50 milliliter size transfer beaker and a teeny tiny 10 milliliter size transfer beaker? I invite you to think about what that implies about chemical reactions. And as we study more in equilibrium, I think the answer to that question will get more and more nuanced and more full as we go along. Thanks for your good work in this lab.